Everything you can see in the night sky, every star, planet, galaxy, and nebula, represents just 5% of what actually exists. The remaining 95% of the universe is completely invisible. We can only detect it through its gravitational effects on the matter we can observe. This isn't speculation or theory, it's measured fact from multiple independent experiments, and it means our understanding of reality is fundamentally incomplete. Imagine looking at an iceberg floating in the ocean. You see the tip breaking the surface, but beneath the waves lies a massive structure, 10 times larger than what's visible. Our universe is like that iceberg, except the hidden portion isn't 10 times larger, it's 19 times larger. Everything we've ever observed, cataloged, and studied, every galaxy in our deepest space surveys, every star in our stellar censuses, every planet we've discovered, all of it combined represents less than 1/20th of what's actually out there. Precision measurements from ESA's Planck satellite, combined with supernova observations and galaxy surveys, consistently show the universe contains roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These invisible components control how galaxies form. They determine how fast space itself expands. They will ultimately decide how the universe ends. The numbers are staggering in their precision. After analyzing temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang itself, Planck's final measurements pinned down the universe's composition to remarkable accuracy. The ordinary matter that makes up stars, planets, and our bodies contributes exactly 4.9%. Dark matter, detectable only through gravity, comprises 26.8%. Dark energy, which drives cosmic acceleration, dominates at 68.3%. Despite decades of searching with increasingly sophisticated detectors, we still don't know what either dark matter or dark energy actually are. Underground laboratories burrow deeper into the Earth, shielding ever more sensitive instruments from cosmic rays. Particle accelerators smash protons together at energies that recreate conditions from the first moments after the Big Bang. Space telescopes peer back through time toward the universe's birth, yet the dark sector remains stubbornly hidden. New space telescopes launching this decade may finally solve the mystery, or they may force us to completely rewrite our understanding of gravity and space-time. The stakes couldn't be higher. We're not just missing a few puzzle pieces. We're missing 95% of the puzzle. In the 1970s, astronomer Vera Rubin was studying the Andromeda Galaxy, our nearest large galactic neighbor. Using the Carnegie Institution's telescopes, she measured how fast stars orbit at different distances from the galaxy's center. What she discovered would revolutionize our understanding of the cosmos. Rubin found that stars were moving too quickly to be held together by visible matter alone. Her rotation curve measurements showed stars at the galaxy's edge moving at roughly the same speed as those near the center. This was completely contrary to what Newton's laws predict for visible matter. It was like watching ice skaters on a cosmic rink, all spinning at the same speed regardless of how far they were from the center. In our solar system, the physics is straightforward and predictable. Planets farther from the Sun orbit much more slowly. Mercury races around its orbit in 88 days, whipping through space at 47 kilometers per second. Distant Neptune crawls along at just 5 kilometers per second, taking 164 years to complete a single orbit. This follows a simple rule discovered by Johannes Kepler 4 centuries ago. The farther you are from most of the mass, the slower you should move. But galaxies don't follow this rule. Instead of dropping off with distance, orbital speeds in galaxies remain nearly constant, far beyond where most stars end. It's as if some invisible mass extends far beyond the visible galaxy, providing the gravitational glue to hold everything together. Rubin's data showed that if galaxies contained only the stars and gas we could see, they should have torn themselves apart billions of years ago. The outer stars were moving so fast they should have escaped into space like rocks flung from a sling, yet there they were, held in stable orbits by some invisible gravitational anchor. The implications were inescapable. Either our understanding of gravity was wrong, or most of each galaxy's mass was invisible. Fritz Zwicky had noticed similar problems in galaxy clusters as early as the 1930s. Working at the Mount Wilson Observatory, the Swiss astronomer measured the speeds of galaxies within the Coma cluster. Like Rubin's stars decades later, these galaxies were moving too fast to be gravitationally bound by what we could see. Zwicky calculated that the cluster needed 10 times more mass than was visible to hold itself together. He called this missing mass Dunkel Materie, dark matter. For decades, most astronomers dismissed it as an oddity, an anomaly that would eventually be explained away. They were wrong. The anomaly was real, and it was everywhere. The bullet cluster collision provides the most dramatic evidence that dark matter is real. This cosmic train wreck occurred when two galaxy clusters, each containing hundreds of galaxies, smashed into each other at speeds of several thousand kilometers per second. X-ray images show hot gas, which holds most of the visible matter, lagging behind during the collision. The gas was slowed by drag as the two clusters smashed together, like two cars crashing and their contents flying forward. But gravitational lensing maps reveal that most of the actual mass passed straight through, aligned with the galaxies, not with the gas. The lensing acts like a cosmic magnifying glass, bending and distorting the light from background galaxies. By measuring these distortions, astronomers can map where mass actually exists, regardless of whether it glows. This separation is smoking gun evidence. The visible matter and the invisible matter behaved completely differently during the collision. Dark matter, whatever it is, barely interacts with ordinary matter or even with itself. It's like a ghost that only reveals itself through gravity. During the collision, the dark matter particles passed through each other and through the hot gas as if nothing was there, while the gas slammed into itself and heated up to hundreds of millions of degrees. Planck's final analysis of cosmic microwave background patterns gives a matter density parameter of approximately 0.315. Baryons, ordinary matter like protons and neutrons, contribute only 0.049. This means dark matter outweighs ordinary matter by more than 5 to 1. For every kilogram of ordinary matter in the universe, there are more than 5 kilograms of dark matter. The cosmic microwave background itself tells this story with exquisite precision. These ancient photons, released when the universe was only 380,000 years old, carry the imprint of sound waves that rippled through the primordial plasma. The pattern of hot and cold spots in this radiation reveals the universe's composition like a cosmic fingerprint. The data is so precise that astronomers can determine the relative amounts of ordinary matter, and dark energy to better than 1% accuracy. Gravitational lensing surveys reveal a cosmic web of dark matter filaments spanning billions of light-years. These form the invisible scaffolding on which all visible structures hang. The filaments stretch across the cosmos like a three-dimensional spiderweb, with galaxy clusters sitting at the intersections where multiple filaments meet. Without dark matter's gravitational pull, galaxies as we know them simply couldn't exist. The universe would be a sparse collection of isolated stars with no large-scale structure. Computer simulations show this clearly. Run the cosmic clock forward without dark matter, and you get a universe nearly empty of galaxies. Ordinary matter alone lacks the gravitational oomph to pull itself together into large structures before cosmic expansion dilutes it too much. Add dark matter, and the cosmic web emerges. Dark matter clumps first, creating gravitational wells. Ordinary matter falls into these wells like water flowing downhill. Gas clouds collapse, stars ignite, galaxies light up. The universe we see is built on a foundation we cannot see. The simulations are remarkably detailed. They track billions of dark matter particles through cosmic time, watching as tiny density fluctuations grow into the massive structures we observe today. When astronomers compare these simulations to real galaxy surveys, the match is stunning. The cosmic web predicted by dark matter models matches the observed distribution of galaxies with extraordinary accuracy. But what exactly is dark matter? After decades of searching, we have a shopping list of candidates, each more exotic than the last. The leading contenders include WIMPs, weakly interacting massive particles, in the GeV to TeV mass range. There are ultralight axions, originally proposed to solve quantum chromodynamics problems. and sterile neutrinos that interact only through gravity. WIMPs are the most studied candidates. They would have roughly the mass of heavy atomic nuclei, but interact only through the weak nuclear force and gravity. In the early universe's hot, dense conditions, they would have been created in just the right abundance to match today's dark matter density. It's an elegant scenario. As the universe cooled and expanded after the Big Bang, WIMPs would have fallen out of thermal equilibrium with ordinary matter, leaving behind a relic abundance that perfectly matches observations. The physics is compelling. WIMPs would be their own antiparticles, occasionally annihilating when they collide and producing detectable radiation. They would interact with ordinary matter just strongly enough to have been produced in the right quantities in the early universe, but weakly enough to remain invisible today. It's a Goldilocks scenario, not too strong, not too weak, but just right. The Lux Zeppelin experiment uses 7 tons of liquid xenon 1.5 kilometers underground in South Dakota. Buried beneath layers of rock in the former Homestake gold mine, the detector sits in one of the quietest places on Earth. In 2024, it reported the world's most sensitive search for WIMPs. The result? Absolutely nothing. The underground location is crucial. Cosmic rays constantly bombard Earth's surface, creating showers of particles that could mimic dark matter signals. But deep underground, only the most weakly interacting particles can penetrate. The rock above acts like a cosmic filter, screening out everything except neutrinos and hopefully dark matter. Zenont in Italy's Gran Sasso laboratory achieved even tighter constraints. In February 2025, it set an upper limit of 1.7 times 10 to the minus 47th square centimeters for WIMP interactions. This cross-section is so small it's almost incomprehensible. A WIMP could pass through a light year of lead and probably never hit a single atom. To put this in perspective, if a proton were the size of a basketball, a WIMP interaction would be smaller than a marble. At CERN's Large Hadron Collider, the ATLAS and CMS detectors search for dark matter particles created in proton collisions. They look for telltale missing energy signatures where invisible particles carry away momentum. When protons collide at nearly the speed of light, they create conditions similar to those in the first moments after the Big Bang. If dark matter particles can be created, this is where they should appear. The detectors are marvels of engineering. They track charged particles with precision measured in micrometers, reconstruct particle trajectories from millions of collisions per second, and identify the signatures of exotic particles that exist for less than a trillionth of a second. But these searches have also come up empty. If WIMPs exist, they're either much heavier than expected, or they interact even more weakly than the most conservative predictions. Axion experiments like ADMX use powerful magnetic fields to convert hypothetical axion particles into detectable photons. They scan different frequency ranges like tuning a cosmic radio, searching for the faint whisper of axions converting to light. Axions were originally proposed to solve a puzzle in quantum chromodynamics, why the strong nuclear force doesn't violate certain symmetries, but they also make excellent dark matter candidates. The experiments are exquisitely sensitive. They can detect single photons emerging from the quantum vacuum, distinguish real signals from thermal noise, and scan parameter space with unprecedented precision. So far, they've heard only silence, but the search continues, probing new frequency ranges and pushing sensitivity to ever lower levels. The null results are actually scientifically valuable. They're systematically eliminating vast regions of parameter space where dark matter particles could hide. Each negative result makes the remaining possibilities more constrained and more exotic. The parameter space for simple WIMPs is shrinking rapidly. If dark matter consists of WIMPs, they must be either much heavier or much lighter than originally expected, or they must interact through entirely different mechanisms. Some physicists are beginning to wonder if dark matter interacts even more weakly than predicted. Others question whether we're looking for the wrong type of particle entirely. Maybe dark matter consists of primordial black holes formed in the early universe. Maybe it's made of axions so light they behave like waves rather than particles. Maybe it exists in a hidden sector of physics, interacting only through exotic forces we haven't discovered yet. The underground detectors keep getting bigger and more sensitive. Plans are underway for next-generation experiments with hundreds of tons of target material. But dark matter remains stubbornly hidden, like a cosmic game of hide-and-seek where we're not even sure what we're looking for. On January 8, 1998, Saul Perlmutter stood before a packed auditorium at the American Astronomical Society meeting in Washington, D.C. The announcement he was about to make would change everything. The universe's expansion was accelerating, not slowing down as everyone expected. Accelerating. The discovery would shatter our understanding of cosmic evolution and introduce an even more mysterious component to the universe's inventory. Two independent teams had spent years using Type 1a supernovae as cosmic standard candles to measure expansion rates across cosmic history. These stellar explosions are remarkably consistent. When a white dwarf star accumulates enough matter from a companion, it explodes with nearly identical peak brightness every time. This makes them perfect cosmic lighthouses for measuring distances across billions of light-years. Perlmutter's Supernova Cosmology project and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees expected to measure how much cosmic expansion was slowing down. Gravity from all the matter in the universe should gradually break the expansion left over from the Big Bang. The only question was whether there was enough matter to eventually halt expansion entirely, or just slow it down. Instead, distant supernovae appeared dimmer than predicted. This meant they were farther away than they should be in a universe where gravity was gradually slowing the expansion. Something was not just preventing deceleration, it was actively pushing space apart. The implications were staggering. This discovery required something with negative pressure, something that creates a repulsive gravitational effect. In Einstein's theory of general relativity, it's not just mass that creates gravity. Energy and pressure also curve spacetime. Positive pressure, like that inside a star, enhances gravitational attraction, but negative pressure creates gravitational repulsion. They dubbed it dark energy. Current measurements show it makes up approximately 68% of the universe's total energy density. Unlike matter, which gets diluted as space expands, dark energy maintains constant density. As the universe grows larger, there's more space, and therefore more dark energy. Its repulsive effect grows stronger over time. Einstein had originally included a cosmological constant in his equations to allow a static universe. When Edwin Hubble discovered cosmic expansion in 1929, Einstein called the cosmological constant his biggest blunder. He thought he had missed the chance to predict the expanding universe. Ironically, this constant is now the simplest explanation for dark energy. Einstein's blunder may have been his greatest insight. Joint analyses of cosmic microwave background data, baryon acoustic oscillations, and supernova measurements find dark energy's equation of state parameter consistent with -1. This matches Einstein's cosmological constant to within a few percent. The agreement is remarkable. After decades of increasingly precise measurements, dark energy behaves exactly like Einstein's cosmological constant. But we still don't know what it actually is. The cosmological constant represents the energy density of empty space itself, the quantum vacuum. Quantum field theory predicts that even empty space should have energy, as virtual particles constantly pop in and out of existence. But when physicists calculate how much energy the vacuum should have, they get an answer that's larger than the observed dark energy density by a factor of 10 to the 120. It's the worst prediction in the history of physics. Unlike matter, dark energy doesn't dilute as space expands. Its density remains constant, so its repulsive effect grows stronger over time as the universe gets larger. This means dark energy will ultimately win the cosmic tug-of-war against gravity. About 5 billion years ago, dark energy began to dominate the universe's evolution. Before that, matter dominated, and cosmic expansion was slowing down. After that, dark energy took over, and expansion began to accelerate. The implications are staggering. Dark energy will determine how our universe ends. Current data strongly favor a scenario called the Big Freeze. The universe will expand forever. Galaxies not gravitationally bound to us will eventually disappear beyond our cosmological horizon. Star formation will dwindle as gas gets too dilute to collapse. Stars will die. The universe will become cold, dark, and dilute. But what if we're wrong about dark matter and dark energy? What if gravity itself behaves differently than we think? This isn't idle speculation. The precision of modern cosmological measurements has revealed cracks in our standard model that may require radical solutions. Mordechai Milgram's modified Newtonian dynamics, MON, proposes that gravity behaves differently at extremely low accelerations. Below 10 to the minus 8 centimeters per second squared, gravity becomes stronger than Newton predicted. This is roughly the acceleration needed to go from 0 to 60 miles per hour in about 7,000 years. It's an almost incomprehensibly small acceleration, far weaker than anything we experience in daily life. MON naturally produces the flat galaxy rotation curves that led to dark matter's discovery. It predicts the Tully-Fisher relation where galaxy mass scales as the fourth power of rotation velocity. For individual galaxies, MON networks remarkably well. It makes specific, testable predictions that often match observations better than dark matter models. The theory emerged from Milgram's careful study of galaxy rotation curves in the early 1980s. He noticed that the discrepancy between predicted and observed rotation speeds always appeared at roughly the same acceleration scale. This wasn't a coincidence, he argued, but a clue that gravity itself changes behavior at low accelerations. However, MON struggles with the bullet cluster's separated gas and gravitational lensing signatures. It cannot easily explain the detailed cosmic microwave background patterns without invoking something very similar to dark matter anyway. Most cosmologists remain convinced that dark matter is real, but MON's successes on galaxy scales keep it in the running as a viable alternative. But cracks are appearing in our cosmological model. The Hubble constant tension represents a major problem. Planck satellite measurements give a Hubble constant of approximately 67.4 kilometers per second per megaparsec. Local distance ladder measurements find approximately 73 kilometers per second per megaparsec. This is a disagreement of over 5 sigma, astronomically unlikely to be a coincidence. In particle physics, 5 sigma is the gold standard for discovery. It means there's less than 1 chance in 3.5 million that the result is a statistical fluke. When applied to the Hubble constant tension, it suggests either unaccounted systematic errors in our measurements or that our standard model of cosmology is fundamentally incomplete. The Dark Energy Spectroscopic Instrument collaboration found a Hubble constant of approximately 68.5 kilometers per second per megaparsec using baryon acoustic oscillations. This supports Planck and deepens the tension with local measurements. DESI's measurement comes from studying the cosmic web's structure, using sound waves frozen into the galaxy distribution as standard rulers. Some modified gravity models are specifically designed to resolve this tension. They change how space expands at late times, potentially reducing the disagreement to within 1 sigma for certain parameters. These models typically invoke new fields or forces that become important only recently in cosmic history. The persistence of this tension suggests either unaccounted systematic errors in our measurements or that our standard model of cosmology is fundamentally incomplete. Other anomalies are emerging. The S8 tension involves measurements of how clumpy matter is on large scales. Different probes give slightly different answers, again at the level of multiple sigma. The Hubble tension and S8 tension together suggest that our standard cosmological model may be missing important physics. ESA's Euclid telescope, launched in July 2023, will map the three-dimensional distribution of galaxies and dark matter over more than a third of the sky. Its 6-year mission represents the most ambitious dark universe survey ever attempted. From its perch at the second Lagrange point 1.5 million kilometers from Earth, Euclid will observe billions of galaxies with unprecedented precision. Euclid's first public data release in March 2025 covered just 0.5% of its ultimate survey area. It already contained data on 26 million galaxies, some over 10.5 billion light-years away. The final catalog will contain measurements of billions of galaxies. Each galaxy becomes a probe of cosmic structure, its shape slightly distorted by the gravitational pull of intervening dark matter. The mission will measure tiny distortions in galaxy shapes caused by gravitational lensing. These distortions are incredibly subtle, typically less than 1% changes in ellipticity, but across billions of galaxies, They will create the most detailed map ever of how dark matter is distributed throughout the universe. It's like using millions of cosmic funhouse mirrors to map the invisible scaffolding of reality. NASA's Nancy Grace Roman Space Telescope completed hardware integration in 2025. It will begin operations around 2027 with a field of view 100 times larger than Hubble's infrared camera. This enormous field of view will allow Roman to survey vast areas of sky quickly, discovering supernovae and measuring their properties with unprecedented efficiency. Roman will discover and monitor tens of thousands of supernovae. This will extend the cosmic distance ladder further back in time to track dark energy's behavior over cosmic history. The mission will determine whether dark energy's strength has changed over the past 10 billion years. If dark energy is truly Einstein's cosmological constant, it should remain perfectly constant over time. Any variation would point to more exotic physics. The James Webb Space Telescope is recalibrating local distance measurements using improved observations of Cepheid variables and red giant branch stars. These observations may help resolve the Hubble tension by either confirming the local measurements or revealing systematic errors. Webb's infrared vision can peer through cosmic dust that obscures optical observations, potentially eliminating one source of systematic uncertainty. Together, these missions will determine whether dark energy's equation of state has changed over time. They will test whether gravity follows Einstein's predictions on cosmic scales. They may potentially distinguish between dark energy and modified gravity explanations. The next decade will be transformative for cosmology. If dark energy behaves like Einstein's cosmological constant, the universe faces a big freeze. Eternal expansion will lead to a cold, dark, dilute cosmos, where star formation eventually ceases entirely. The last red dwarf stars will burn out in 100 trillion years, their nuclear fuel finally exhausted. Black holes will slowly evaporate via Hawking radiation, taking 10 to the 67 years for solar mass black holes and 10 to the 100 years for supermassive black holes. In 10 to the 100 years, even protons may decay, leaving only a thin soup of elementary particles in an ever-expanding void. It's a lonely fate for the cosmos, but it's also unimaginably far in the future. The universe is currently 13.8 billion years old. The Big Freeze scenario plays out over timescales that dwarf the current age of the universe by factors of trillions upon trillions. Entire cycles of stellar evolution, from birth to death, will repeat countless times before the final fade to black. After decades of increasingly sophisticated measurements, we know with remarkable precision that 95% of the universe consists of dark matter and dark energy. But we still have no idea what either one actually is. The underground detectors keep getting more sensitive. The space telescopes keep getting more powerful. The particle accelerators keep probing higher energies. Yet the dark sector remains stubbornly hidden. We've mapped the cosmic web with exquisite detail, traced dark matter's gravitational effects across billions of light years, and measured dark energy's influence on cosmic expansion to percent-level precision. But the fundamental nature of these components remains as mysterious as when they were first discovered. It's as if we've become experts at tracking ghosts without ever seeing one. The Hubble tension suggests our cosmological model may be incomplete. The continued success of MOND on galaxy scales keeps alternative gravity theories in play. We may be on the verge of the greatest scientific revolution since quantum mechanics and relativity. The next decade will determine whether we're missing new particles, new forces, or entirely new physics. Within the next decade, Euclid and Roman will either confirm that dark matter and dark energy are real substances waiting to be discovered, or force us to accept that our understanding of gravity and space-time is fundamentally wrong. Either outcome would represent one of the greatest scientific revolutions in human history. We stand at the threshold of discoveries that will reshape our understanding of reality itself. The universe has surprised us before. It surprised us with its expansion. It surprised us with its acceleration. It surprised us with its dark components. Each surprise has revealed new depths to cosmic mystery. The next surprise may be the biggest yet. We thought we understood the universe. We cataloged its stars and galaxies. We measured its age and size. We traced its evolution from the Big Bang to the present. But it turns out we were studying only the tip of an enormous cosmic iceberg. 95% of reality was hidden beneath the surface, invisible to our instruments, detectable only through its gravitational fingerprints. The question isn't whether we'll solve the mystery of the missing 95%. The question is whether the answer will be more incredible than the mystery itself. In a universe where most of what exists is invisible, where space itself is accelerating apart, where our most fundamental theories may be incomplete, we're about to discover just how strange reality truly is. Perhaps we'll find that dark matter consists of exotic particles from dimensions beyond our own. Perhaps we'll discover that dark energy represents the quantum heartbeat of space-time itself. Perhaps we'll learn that gravity behaves differently on cosmic scales, requiring us to rewrite Einstein's equations. Or perhaps the truth will be something even stranger, something we haven't yet imagined. The cosmos has spent 13.8 billion years keeping its deepest secrets. But the age of cosmic mystery may finally be coming to an end. The next chapter in humanity's greatest detective story is about to begin.